Let me give you like kind of an update on how it's going to go down. So this is we got 2 weeks of class left. So I will give you one more homework, which will be due finals week. Or if you're having trouble getting caught up on your homework, some of you are behind. As is my grading because I've been waiting on some people, but I'm going to get that finished up for the ones that turn stuff in. But anyway, if you have trouble getting caught up, just let me know. It is very likely that we can meet during finals week, which is what I'm supposed to do if I don't have an exam. I don't have an exam for you all. So it'll just be kind of a fun day. We'll maybe talk about some stuff or whatever. I'm not going to keep you here for 3 hours. So any questions? Okay, so the last time we talked about this notion of linearly independent automorphisms, and we proved that if you have a distinct set of linear automorphisms or of automorphisms over the field F, then they are linearly independent. Let me define what we said, or what's part of the title of this, what we're doing now, these cyclic extensions. Let's let F be let F be Galois over K. So F is a field extension of K that's actually Galois over K. We say that F is cyclic, respectively, if the Galois group of F over K is cyclic, respectively. So sometimes you will hear the terminology, oh, such and such is a cyclic extension, such and such is an abelian extension. Really what that means is they're saying 2 things, Galois, and the Galois groups have those properties. They're either cyclic, abelian. So here is kind of a neat theorem concerning cyclic extensions. 8.7.6. Let F be cyclic of K over K of degree N. So let me remind you, of course, cyclic extension, that means that F is a Galois extension over K, cyclic of degree N. So it's cyclic, Galois group cyclic. And so the order of the Galois group is N, which is the same as the degree of the extension in this case. Let U be an F and sigma a generator of Galois group. So sigma is some automorphism that generates it. I know it exists because it's a cyclic group, and U is some random element of the field. Number 1, trace U is 0 and only if U is of the form minus 6 for some U and F. And here is an exact analog of this multiplicatively. This one is popularly referred to as Hilbert's Theorem 90. The norm. Okay, the trace, remember, the trace for Galois extensions, the trace is the sum of the conjugates, right? The norm is the product of the conjugates. So 0 is to trace as blank is to norm. 1, exactly. The norm is 1 if and only if U is V. Let's get this right. Notice the analog, the operation here from trace addition. This is the inverse of additive inverse of sigma V. This is the analog. It's the kind of multiplicative inverse of sigma V for some V. Okay, so let's go through. I'm going to leave the back half of Hilbert's theorem 90 as an exercise, but doing the first part or doing statement 1, I think will show you pretty much exactly how to do it, because basically you've got to go through and exchange the operations plus and minus for multiplication and division. Okay, so let's kind of go through this proof. Let's tackle the first statement first with trace. One way is actually fairly easy. So if it's fairly easy to see that the trace of this is 0, because the trace honestly, let me stick with my notation. Thing. Now the trace is additive, right? That is to say, this is one of the properties of trace. And this first trace is, let's see what we see at the end. Let's see. Well, let's see, 0 to minus 1. Oh no, I need to transfer all these. It's not bad. So what's the trace of V? It is right, because remember this is cyclic, right? And so this is just all the powers. Sigma to the 0 powers the identity, then sigma squared, and that goes through I equals 0 to n minus 1, that goes through the entire gamma logarithm minus that. Right. Now, what happens here? Here's the sum of all conjugates of V. Notice this just goes through all the powers of sigma acting on V, right? Adds them up. And this is the exact same thing. It's just shifted. The index is, in this case, power. The superscript is shifted by 1, so you get 0. Because this outcome and this outcome are the same. 0 topological. Everybody okay? So if you get something of that form, not too bad, right? I mean, the trace has 0. The interesting part of this theorem, of course, is the fact that anything that has trace 0 must be at that point, right? That's kind of really the meat to this, I think. So let's go that. So let's suppose that the trace of u is 0. So in the remainder of this, I'm going to get rid of the subscript, superscript, K and F, because I'm just going to assume that we've got that already. So what we first want to do is first choose I want to pick an element, W, such that the trace W is 1. Now, how do I know that I can do that? Right, I kind of pull that one out in there. How do I know I can find some W that the trace is 1? Well, let me kind of justify that a little bit. We can find notice these are the elements of my Galois groups. These are all distinct automorphisms. The identity, sigma all the way up to sigma n minus 1. These are linearly independent automorphisms. We can find Z and F such that Z plus is not Z. Linear independence guarantees there must be some Z, because otherwise, for every element of the field, that is 0, and that means that the automorphisms are limited. Right? So, how does this help? What we're going to do is we're going to pick W. Now put W is trace Z inverse times Z. Notice here that the trace of W is trace of Z inverse well, W is trace Z inverse times Z, and then take the trace back. Agree? Now, I can pull a trace Z inverse out of this. How did I make that magic work? That's right. And where does trace Z live? It actually lives down in K, right? And so, and trace Z is not 0, so its inverse lives in K. And so remember, you can pull constants from the field K out of it. So it's what you say there. And, oh, okay, here we go. 1. Right. So, all right. So we've got our desired element W that has the property that its trace is 1. So, I think that this is part of his work. I'm going to write down some stuff here. So I want to look at the following element. Let V I want this to be UW plus U plus sigma U. That quantity times sigma W. Uh, plus continue this pattern. W, and you expand U plus sigma W, sigma U plus, and we're going to go out to n minus 2, I guess. U plus sigma U plus sigma squared U sigma n minus 2 U sigma n minus 2. Okay, good. Now, recall price U is equal to 0. All right, that was our assumption in the first place. I'm going to need that coming up. And so when I screw this up, I'll apologize ahead of time, but let's see what happens. Let's try to compute V okay, let's try to do that. Well, I want to go to the trouble to try to repeat V here. It's UW plus U plus sigma U sigma W plus U plus sigma U plus sigma squared U sigma squared W. Keep on trucking until you get U plus sigma U plus sigma squared U plus sigma n minus 2 sigma n minus 2 W. And now we're going to do sigma V. All right. Let me see if I can line this up in an intelligent way here. That's what you practice that. So if I do sigma V, that's going to give me minus. Okay, so it's going to be sigma U, sigma W. So this is going to be so basically subtract applying this to all this. This is plus sigma U plus sigma squared U times sigma squared W plus sigma U plus sigma squared U plus sigma cubed U sigma cubed W up to sigma U plus sigma squared U plus sigma n minus 1 U sigma n minus 1 W. Right. for minutes. So let's try to sort this out. All right. And cross our fingers. Well, how about this? I've got a UW. All right. Check a moon code. And now, what else do I got? Well, I've got a U sigma W. From this. And then I've got sigma U sigma W, which will cancel this, right? So those are done. Agreed? Okay, let's keep hoping this kind of works out. Notice I think I'm picking up a pattern here because now I've got sigma U, sigma squared U, sigma squared W, and that's going to cancel out this chunk. These last two terms of this are going to cancel with this. Agreed? And that's what's going to be left over when it's all standing is. Agreed? And notice this chunk here, I don't have the one written up here, but this will, the next one's supposed to have 4 terms. These 3 will cancel the last 3 of this, and I will be left with U sigma cubed W. Agreed? Okay, this has n minus 1 terms. This has n minus 1 terms. Well, I guess let's see. Kind of match on this. Right, so I should be left with a U sigma n minus 2 W. And finally, I guess I'm left with this one didn't have any sigma n minus 1 W's to go to, right? So I'm left with this junk at the end, which is sigma U plus sigma squared U plus sigma n minus 1 U all times sigma n minus 1 W.
Subtracting them, right?
Thank you, and we should be subtracting them. Okay, where do we go from here? Because there's some more trimming that needs to be done. Anybody see what else is new? Which one? Ready? Very good. So let me make an observation, which I think I'm ripping you off. So we have a U. What does that equal to? 0, because that's the trace of U, right? So I think I did what I want. So this chunk right here, minus sign through it, this should actually be plus U. So this is right. So in return, we have this is actually U sigma W. And that should be plus U sigma n minus 1 W. That's what. this makes this. Everybody okay with it? Now, notice that I've got a common factor Q. And what's this? This is the trace of W. And what do we choose the trace of W to be? I can't believe I didn't follow one bike. Right. So there you go. B minus sigma B. Okay. Any questions? So let me give you a hint for, I promised I'll leave you, Hilbert's theorem, 90 part of it. Okay, the first thing I want to do is notice that if you then the norm, again, I'm going to suppress the superscripts here, is sigma B sigma. And so this is really of course, each one of these sigma to the i's is an automorphism. So this is sigma I B, and this is sigma I sigma B inverse. And so what we get here is the product this first bit and this other product. One sigma to the I and this turns out to be the norm of B, and this is actually the norm. Because really what this did is this is just right. Of course, I can write this as sigma B inverse, and this is actually the norm of B inverse. For the other bit, right, the interesting bit where, okay, now you've got something going one, how do you know it's this form? The meaty part, so to speak. Then what you want to do here is yeah. Find Y and F. Such that B is UY plus U sigma U sigma y plus sigma and the last one is again minus 1 like that. So find a y such that that thing right there is non-zero. And of course, you'll see quickly why you want it to be 0. Then verify that U inverse. So that would be U is B, sigma B inverse. Right, that's equivalent. And that'll give you what you want. Let's see if you can figure that out. And if you get hung up, let me know. Now, Hilbert's theorem 90 is all fun and games. It's kind of nice and applies to cyclic extensions. Let me give you a nice. I cooked up an application that I think is kind of fun, especially if you like number theory. So, example. Short application of focus. Theorem 90. Consider Q sign. So this is the ordinary Gaussian rationals, if you will. So this is all complex numbers that form A plus B, where A and B are rational. Notice that the degree of this extension is 2. And one of the things we actually proved in the homework earlier on is if you have any extension of degree 2, it's Galois as long as the characteristic's not 2. No problem over here because the characteristic's 0, right? And so the Galois group I'll write it explicitly. I'll write 1, and what I mean by that is the identity automorphism. Maybe I can put like a little double 1, so this becomes really fancy. And sigma, where sigma is a familiar automorphism. What is sigma? Complex constant. Okay, so now suppose. Oh, and let me also kind of lay some other groundwork. Let A and B be rational numbers. So A plus BI is QI. The norm is A squared plus B squared, right? It's just take A plus BI, multiply by its complex constant A minus BI, and there you go. Right? In fact, you all probably have seen this in an earlier abstract algebra class where maybe you wanted to prove something was irreducible. How many of you have ever seen that in abstract algebra class where they'll give you something, they'll say, oh, use the norm to show that this thing is irreducible? Yeah, it depends on the abstract algebra. That should be another plug for my class in fall, because we'll look at some of that actually. Now, this is the norm, right? So I did promise you this application over theorem 90. So let's suppose that A, B, and Q and norm suppose I have something of norm 1. So in other words, having an element in QI that has norm 1 is equivalent to saying, hey, look, I've got rational numbers A and B. There's a solution to this equation. Right? Squares both of them. When you add up the squares, they have 1. Well, so by Hilbert's theorem 90, there exists theorem 90, there exists Z such that such that A plus right, where sigma is, of course, complex conjugation, right? Because sigma is, of course, the generator of the Galois, right? Pretty simple because there's only one non-identical element, right? So what does this mean? Well, this is, of course, x plus iy, and this is x minus iy. And we can actually collect the denominators to assume right, because if x is alpha over beta and y is gamma over beta, you can clear all the denominators here, right, and assume that x and y. So given if x and y are rational numbers and a plus bi is equal to rational plus irrational, rational minus irrational, you can also assume that these are integers just by clearing the denominators in the top and bottom, right? And so that's going to make something interesting for us. So A plus BI is, so let me kind of free this up here. I'm going to multiply the top and bottom of conjugate. So in the bottom, I get x squared plus y squared. Sure enough, right? And what do I get in the top? I get a bit of a mess. I get x squared minus y squared. And then I get plus I times 2xy. Everybody agree with that so far? And so I have A Do I agree with it? So in other words, what you're saying is if you have a solution to this, right? You can parameterize the rational numbers of some integers this way. This is a rather famous parameterization of solutions. This turns better. You parameterize the rational points on the circle system A squared plus B squared equals 1. This parameterizes terms 10, right? So nice little application of Hilbert's theorem 90. And I can't resist this as well, but there's another place where this parameterization is actually important. I don't know how to do that integral. Spotlight in here, I'm good at 85-20, but this actually comes out of this. You want to know how to do this? Right, it's very natural. I mean, what's the first thing you're gonna do? Is like it's trying to use this spot, right? That ain't gonna work, right? Because you got that extra sign, right? Some special cases you might be able to do these substitutions. But here's kind of a nice thing that follows actually from this parameterization as well, and you'll see it come up. This is one of the important things about the parameterization circle. This looks very untenable, right? The following substitution always works. Anybody ever seen the substitution before? I look like I've been sniffing the loop or something, right? Where did this come from, right? This is way the heck out of the blue, right? This is called a Weierstrass substitution. And at first it's like, what are you even doing, right? But this substitution always turns quotients of trig functions into quotients of polynomials. And in theory, you can always do quotients of polynomials if you factor them just by doing partial fractions, right? I won't finish this one because I'm sure it's awful. But you should probably do this integral just for fun because you get these crazy integral in terms of inverse tangents and strange things. And there's no way that you're ever going to guess it, right? But why does this work? Well, it's exactly this parameterization. So that's another example. Let me draw a triangle just for fun. I think of x over 2 as my angle. And of course, my goal ultimately is I'm going to turn these sines and cosines, these trig functions, into quotients of polynomials. So t is the tangent of this. So I get this, correct? And so what this means is, this is all very intimately related. What do I want? Well, if I've got this triangle here, notice sine x is 2 sine x over 2 cosine x over 2. Right. Small half angle stuff. And this is 2. Okay, what's the sine of x over 2? Well, that's t over that radical. And the cosine is 1 over that radical. The two radicals get rid of the radicalness and become like, more conservative. I don't know what happens to them. But anyway, this becomes t over t squared plus 1. Okay, so and I can pull a similar trick with cosine because cosine x is cosine squared x over 2 minus sine squared x over 2. Right, doing the old double angle thing, half the angle, right? And this is going to be, well, the cosine is this, you square it. And the sine is this, square it. Right? now I've only got a dx problem, right? But notice that dt using the original substitution is secant squared x over 2 times 1/2 dx. And secant squared, so this is 1/2. Secant squared is tangent squared. X over 2 plus 1 dx. But this thing, of course, is t squared. So dx, it turns out, is 2 dt over t squared x cubed. So in particular, just to look at our applied thing here, this becomes the integral after the substitution of 2t over t squared plus 1, 2 dt over t squared plus 1. And this is going to be 2 cosine x. So this is going to be 2 minus 2t squared over t squared plus 1 minus 2t over t squared plus 1. And actually, this would be a little bit of a mess, right? Because it takes t squared plus 1 squared to clear out the top. And so you'll get like a 4th degree polynomial on the bottom, which is awful. But in theory, you can do it, right? If you can find it. So this turns something that is really untenable into something that is a quotient of 2 polynomials. And this always works because it turns sine x into a quotient of polynomials, it turns cosine x into a quotient of polynomials, and it turns dx into a quotient of polynomials, and so it turns all trig functions into a quotient of polynomials. We do it. And you should see something familiar. This is yet another important application of the parameterization. So, how many of you have ever seen this substitution? Yeah, it's kind of a, unfortunately, computers have made our lives less fun in some ways. There's also one actually with hyperbolic trig functions as well. Okay, any questions? Here's something that I have thrown around for you a little bit, use this terminology. I'm going to formalize it here, and then that will probably be close to good. Definition 878. We say that tornado is a primitive root of unity if okay, this is what makes tornadoes an nth root of unity right here. What makes it primitive is n is the smallest positive power that does this trick for you. We're going to talk next time about what we call cyclotomic fields. And cyclotomic fields are the special fields you get by joining roots of unity. And in fact, you saw one of those on the homework when we did all the ones with the Galois group. The polynomial, I think it was x to the 6 minus x cubed plus 1 that you did. That actually, that one is actually a primitive 18th root of unity. As a matter of fact, it turned out of that polynomial. We'll talk more about this next time. Any questions? Questions? All right. Well, I will catch you all on the flip side then.